Welcome to Lesson 21, Learn C Programming on the Raspberry Pi. Well, last day we did some programming using software pulse width modulation. And I also introduced you to several new tools that I use when I do programming on the Pi or when I build little projects on the Pi. And what I'd like to do today is just to use those tools again to show you what I do, and also to do an example using a tricolor LED. Actually, sometimes they call them RGB LEDs, red, green, blue LEDs. So let's start first by I'll show you a circuit. I'll draw a circuit. I'll use the tool we used that I introduced you to last day, which is called GNOME Diagram Editor. So I'll start that up, and now we're going to use a tricolor LED. Well, a tricolor LED is really three LEDs encased inside one housing or one case. So why don't we just take a vertically aligned LED here, and I'll just put it here like this, and then I'll just copy it 3 times. Paste and paste. So we could pretend, for example, that these 3 LEDs are inside one casing, which I have down here on my little breadboard. And again, this is called a RGB LED, red, green, blue. And if you look, the cathode here are the negative side, and the anodes are the positive side. Well, what I have here is a common anode LED. So the wiring for this is going to be a little bit different. Since we don't have common cathode means we just put the cathode to ground. But in this case we have a common anode, so I'm going to tie that common anode with this yellow wire to the 3.3 volt pin on the Raspberry Pi. So if I take these 3 lines here, and I can just take a line and I can just connect them all like that, and then I can take that and I can say, well, for example, maybe another line like this, and I could just say that's my 3.3 volts. So I'll put a text box there, and I'll just say that's 3.3 volts. Let me make that a little bit bigger so we can see it more clearly. Maybe put it up to about 48 points. Okay, so this is our 3.3 volt line, and then And then the three colors, red, green, and blue, are going to be, I have three wires here, red, green, and blue, and they're just going to be tied to GPIO pins 23, 24, and 25. But they're going to go through three resistors. So I could take a resistor here. Wonder if I have a I guess I don't have a vertically aligned, oh yes I do right here, vertically aligned resistor. So I could take that and I could just plop it down here. And again, I could just duplicate it. So I'll just copy it here. Copy, edit, and I'll say paste. And paste once more. And so I can just take my three resistors and connect them up like that. And then each one of these resistors will go to a GPIO pin I have here. So let me put a text box up there. I'll just copy this guy. And I'll just say here, so for example, I could just say GPIO 23, and that could be GPIO 23, for example. And copy and paste. And this could be GPIO 24. I could put that over here. And then I could do one more. And that could be GPIO 25. Put that over here. So that's the diagram I have right here built onto this little red breadboard. And these are, I believe I'm using here 270 ohm resistors. Okay, so you can see how if you got something really complicated, you could actually build it using this DIA tool, DIA, the GNOME diagram tool. Now you could save it. You can later on use it. I won't bother saving this because it's fairly trivial. We don't need it. So I'll just exit this, close it, discard the changes, so I don't want to bother saving it. And I'll just close this editor. Now the other tool that we used was a tool called fritzing, F-R-I-T-Z-I-N-G. So let me just go over that with you. The fritzing tool. And so we can just bring up the breadboard view like that. It's a little too large, so I'll just make it smaller here. And then what I can do is I can bring in the Raspberry Pi right here. And I can then go to do a search for an LED. And what I'm looking for here in the parts bin is a tricolor LED. Or actually I should have probably searched for RGB. do a search for RGB, red, green, blue, and you can see here I have one here, which is the four-leg LED. There you go. So if I could make it just a little bit bigger here so you can kind of see it. Okay, so I have my LED, and if I position the mouse pointer, you can see here this is the red cathode. This is the common anode. So the common anode went to 3.3 volts. So I can just go here. 3.3 volts is this pin right here. Let's say I have it right there. And I can just take that, say 3.3 volts, and I can bring it right to the common anode, which is right there. Okay, and I can change the color to match up my diagram here. I'll change it to yellow. Okay, so that matches up this guy here. Then of course I have this line here is red, so that one goes to GPIO 23. So I can take GPIO 23. If you see here 23, 24, and 25, if you look closely you'll see the three of them. So 23 is right here, and that would go to the red one. It's going to have to cross over top of the yellow, but that's fine. This there. So I'll just go here, and it will go to the red one. And I'll change that color to red. So that's GPIO 23. It shows right here. And then of course the other pins over here. What do I have here? Green is this one here, so that goes to 24. So I'll just make a line up there to that one, and that's the green line. I'll change the color to green, and the last one is 25, so we skip a pin here, we go to 25, and I do this last one like that, and I'll change it to blue. Okay, so there you have it. So that's basically, this is the same as what I have here on my little red breadboard. Okay, so a little fast introduction, quick introduction to using fritzing, and also using DIA for planning out your projects. Again, I'm going to close this. I won't bother saving it. Like I said, it's a little too trivial to save. So I'll just close it and say don't save. And that's it. Okay, so let's now go back and do some coding here. I'll bring up Genie. And while I'm waiting for that, I'll go to lessons, and now I need a directory for lesson number 21. Lesson 21. And if you look at our last day, we had a green light on pin 21, or on GPIO 21, and what we did was we used soft PWM create function to create a software pulse width modulation enabled GPIO pin, that goes from 0 to 100. And then what we did was we just had 2 for loops to have the LED go from 0 brightness to maximum brightness, and then go from maximum brightness back down to 0 brightness, and it would take 20 seconds, 10 and 10, to do the whole thing. Okay. Well, now we have a tricolor LED, so we're going to have to modify this. Let me first I'll open up a new project. Okay, so let's start a new program here. See if we can get this RGB LED to light up. So we'll just start typing and see what happens. First, we have to include the wiring pi header file. Then the software pwm.h header file. And then we need to set up our 3 GPIO pins. So red will be GPIO 23, green will be GPIO 24, and blue will be GPIO 25. And here's our main. Okay, well, we're going to need a counter here for our loops. So just set up an integer I. And then we have to set up the wiring pi library. Pi I'm not going to bother in this example to check if we are root or not. So I'll just run it with sudo, and hopefully things will work out. Next, we have to create 3 software PWM pins. So let's do that here. Soft PWM create. So for the red, 0 to 100. Now this is interesting because I want to put a comment up here to say we are using our RGB LED uses common anode. Remember that the anode line here is tied to 3.3 volts. The yellow line here is tied to 3.3 volts. So, you know, this is a different kind of setup. What that means is that when we put 0 volts onto the red line, we're going to have 0 volts here, but on the other side we're going to have 3.3. So the potential difference will cause current to flow and light up the LED. So 0 here means basically 0 volts, but because we have common anode, it means that we are turning the light on fully. Whereas with 100, we're setting the voltage to 3.3 volts on the red line. So once we get 3.3 volts on the red line, and then we always have 3.3 volts on the yellow line, the common anode, then 3.3 here and 3.3 here, potential difference is 0 and no current flows. So with 100 here, If we set it to 100, we turn the LED off. So that's an important difference when we're using common anode as opposed to common cathode. Okay, now that that's explained, we'll create our other two PWMs here, this one and one more. Now this one has to be our green one, and this next one is our blue one. Okay, now what I want to do is I want to test it. For example, maybe we want to test the green light to see if we can turn it on and off and vary its intensity. So I want to turn the red one and the blue one off. So I'll say soft PWM right, red 100. Remember that putting full voltage on the red line, full voltage here, 3.3 volts on the red line, 3.3 volts on the yellow line, potential difference is 0 volts, so there's no current. So that basically, this basically turns the red light, the red LED off. Let's also turn the blue one, soft PWM right. We'll also turn the blue one off. So I'll just put a comment here, turn red off, and also turn blue off. Now once we do that, we can go into our for loop, and we can say for I equals 100, I is greater than or equal to 0, I plus plus. And what we'll do is soft M right grn comma I, and then we'll just pause for let's say 50 milliseconds. So you notice this loop here, we start with full voltage on the green line, full voltage on the green line, and full voltage on the yellow line means no voltage across the LED, so no current flow. So we start with the LED being off, and then we increase slowly. Actually, this is wrong. I should have put minus minus. We want to slowly decrease the voltage. As we decrease the voltage on the green, the potential difference between the yellow and the green keeps growing, and the light gets brighter and brighter. So when we come out of this loop, the green light is maximum brightness. So let's now just pause for a bit here. Let's say we'll delay for half a second. It's 500 milliseconds, and then we'll do the loop to darken the green LED. So this time I'm going to start at 0. So it's going to be the opposite of what we had up here. Start at 0, and then I'm going to say I is less than or equal to 100, and I plus plus. So what we're doing in this loop is, with I as 0, what it means is that we have 0 volts on the green, which is what we ended up here, and we have maximum potential difference on the LED, so we have maximum current flowing, the LED is bright, and then we slowly bring this I up to 100, which means 3 volts here, 3 volts there, and 0 potential difference and no current flowing. So that should just about do it. And we can say return 0, and we can just finish the program. So let's save this guy and see if it works. Save as, we'll save this in lesson 21, and I'll call it soft PWM RGB.c. Okay, so down here we now have it. So let's compile. GCC. Our output is going to be soft PWM RGB minus L wiring pi, and you notice we also need to include the pthread library. Minus LPTHREAD, pthread. And let's hope it compiles, which it does. So there we have our executable. Now we'll talk about threading in some later lesson in this whole course, but right now you don't really have to know it or understand it. If you want to do some reading, you can go, by all means, go ahead and do so. Anyway, so let's run this guy. Sudo /soft RGB and see what happens. So there the light is going up to maximum green, and once it hits maximum green, then it starts to go into the second loop, and it goes down to minimum green and it turns off. Okay, so you can see what happened there. We can try it again. Let's move this guy over a bit here so we can actually see the code. And we'll just try once more. So it starts going higher, 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 brighter, brighter, brighter. And once it gets to maximum brightness, it exits this first for loop, and then it goes down into the second loop, and it goes through that. Okay, so it seems to kind of work. In fact, we could try another light just for fun. We could say, let's turn off the green one here. We'll turn the green one off, and then we will do our experiment using the blue. Blue and blue. So we have the red and green are both turned off. I should put a little delay in here. Let's say delay 1/10 of a second after we turn them off. So we have the red and green are both turned off, and now we're going to do our experiment using the blue. We can do that. Save it, and we can recompile. There we go. And we can now run it. And we should get the blue light coming on. And it is a blue light, and then it goes off. Boom. And it's done. Okay, so then we could do a test on the red by turning the green and the blue off, and so on. In fact, so using this technology here with a RGB light, we can have any color we want. So just for fun, why don't we make another program where we can write a function. We'll do that. Hopefully this won't take long. Let's make a new program here, and we'll take the old one and we will cut and paste probably just up to here. That's all we'll need in the new program. Okay, and what we'll do is we'll make a function where we can make any color we want. So for example, let me turn all the lights off first of all. Soft PWM, right, red, 100. Remember, 100 turns it off. Okay, so we'll turn them all off. Put another one here and the other one here. So red, green, and blue. We'll turn them all off, and then we'll just put in a little delay here. Let's delay one second. Then we'll call a function to make a color. Let's just call this, let's say, color. And let's say for the red, well, what happens if we turn the red on? Let's say the red and the green on and the blue off. So let's turn the red on, the green on, and the blue off, like that. And then we'll delay for, let's say, 3 seconds, and then we will turn them all off. We'll turn them all off, 100, 100, 100, like that. And then we will return 0. And that's the end of our main. Well, we have to put in a prototype for a color. Void color, and it's going to take 3 integers, int, like that. So there's our prototype for our color function. So all we're going to do is we are going to, first of all, we're just going to, actually we don't even need these, we can turn them all off using our color function. So let's just do it like that. 100, 100, 100. So that just turns them all off. We stop for a second. We turn the red and green on, and then we stop for 3 seconds, then we turn them all off. And that's our whole program. So we'll just, let's save this guy as, let's say save it as, in lesson 21, we'll save it as, let's say, color-rgb, color-rgb.c, for example. And now we have to write our color function down here. So we can say void color, and I'll say int red, comma, or yeah, int green, comma, int red, green, and blue. Okay, so there's our function, and then all we have to do is just do exactly what it says. So we'll say soft PWM right. So first red will be set to red, and then let's put the other 2 in here, like this and like this, and just return, and that'll be our function color. Green will be set to G, and blue will be set to blue. Okay, save it. And let's see if it compiles. GCC, what do we call this? Color. Minus O. Minus L. Wiring pi. Minus L. P. P thread. Oops. Oh no, we have a crazy character in here where we say void color. Here and here. I don't know how we get these in here. Somehow we get that in there. Let me see if I can just erase all of that. And do it again, because we got some stray characters in there. I don't understand why. Let's try it just by writing it again a second time and see if we can get it right. Void color int R int G int B, and then we can say soft. Just do it once again if this doesn't work well. And red comma R, and we can just repeat that twice, I guess, and repeat it once more, and just do that. So this should be GRN, and that should be G, that should be blue, BLU. So let's save that, save it, and we'll see if we get any kind of these spurious kind of characters in there, and we don't this time. This is just an aside, but sometimes when you're typing and you hit some weird keys like some control characters or something, and those control characters are invisible characters, they're non-printable, but they go into the code anyway, and then the compiler sees them as these weird kind of characters. I think these are in octal, giving you these octal characters. And it says it doesn't really like them on line. This was on line 32, so it's down here somewhere. So I probably hit some key by accident and it put in some character. Anyway, let's see if we can do this. Again, what should this thing do? It should just turn all the lights off. Then it should turn the red and the green on, and then stop for 3 seconds, then turn all the lights off again. So let's see if we get some results here. /color. There you go. So red and green gives you a yellow light, and then it should go off. Why doesn't it go off? Red, green, blue, color. Oh, sorry, 0 volts. 0 volts turns it on. Yeah, right. So this should turn it off. Turn the red and green, and then it should turn them on again. Oh, I think that we needed a pause in there. It's working too fast, I think. So let's make sure we put a pause in here before we do any of this. DELA, delay. Let's delay for 1/10 of a second before we change the color here. Okay, let's see if we can do that. Recompile, and we will run it again and see what we get. Now we get a nice yellow, and it still doesn't want to come off. Doesn't want to turn off for some reason. Red, green, blue. Red, green, blue. Oh, I wonder if we need a delay at the end of that too. Let's try that. Delay 100, like that. Another 1/10 of a second. So give it time to react. And so that goes off, comes on, 1001, 1002, 1003, and then it goes off. This is a good point to note, an ending point for this lesson. This lesson's been dragging on, so it's way too long. The whole point with software PWM is it's slow. So you don't get the efficiency, the speed you can from hardware PWM. So you have to put in little delays here and there to kind of slow things down. Okay, so keep that in mind when you're dealing with software pulse width modulated code, because it's really not really efficient compared to hardware PWM. Okay, this has been going on too long, so I think we'll call it a day. And you can review this lesson, and I'll see you for lesson 22.